It's my pleasure to talk about my work for you. So today I'm going to talk about Dirichlet Eigenvalues and how to optimize the eigenvalues with respect to the geometry of the domain. Maybe this talk doesn't really belong to the program, but I hope that you will find it interesting. So first of all, I'm going to introduce the problem and talk a bit about the history of optimization problems. And then I will talk about my work, which is about the special domain with dihedral symmetry and how really we can put a hole or host obstacle on the domain so we can optimize the eigenvalues. And then after that, I will talk a bit about the second eigenvalue and how to optimize it, and the nodal set of the second eigenfunction. Okay, so we start with this. Since 1877, I think this is a classical result that among all the, if you take a lot of drums of given area, the one that has the least eigenvalue, this is the circular one. So here's a list of domains. These eigenvalues were calculated by Lord Rayleigh. So a list of domains, different shapes, but the same area. And you can see that the first one, which was the circle, has the lowest eigenvalue. Okay, so I'm talking about the Dirichlet Laplacian with the sequence of eigenvalues from lambda 1 to infinity. Okay, and the question is, what's the relation between the geometry of the domain and the eigenvalues? Okay. Then the specific question that I'm going to talk about is how we can maximize or minimize one of the lambdas with respect to the geometry of the domain. Okay. So this conjecture of Lord Rayleigh has been proved actually 35 years ago by Faber and by Kiwan. And then another property that if you take all the triangles with like equal area, the one that has the lowest first eigenvalue is the equilateral one. So we can see that when we add symmetry to the domain, the lambda one, like the membrane has less freedom to move, and that's why the lambda one will be smaller. Same thing if we take the set of all the quadrilaters of same area, the square has the lowest lambda one. Okay, and as my knowledge for polygons of n bigger than or equal to 5, this is still open. We don't know. We know that when we take the regular polygon, it has actually the least lambda 1, but we don't have an actual proof of this. There is only numerical proof, but not a mathematical work on that. Not really pure mathematical work. Okay, now let me talk about the second eigenvalue. If we take the set of all domains with equal area, the one who has the lowest lambda 2 is not a circle, but actually the union of two circles. This was really surprising, or this result. And then if we want to add the condition that we want our domain to be convex or connected or something like that, because the union of two circles, two disks, this is not connected, it's not convex.
So you mean the union of two disjoint disks? Mm-hmm. Yes.
Mm-hmm.
Yeah. So if we add the condition, I want to find, for example, the lowest lambda 2.
There are no minimizer inside the...
Sorry?
There are no minimizer inside the connected domain.
Yeah. So we don't.
But you
It
could
will
make them
look at the
connected
thin tube.
next to each other.
Okay, I see.
You can make them connected, but still it's not open when you connect. It's not an open domain, yeah? And it's not convex not anymore. Okay, and for the highest lambdas, also there are some numerical results for some of the lambdas. It's union of two balls for two disks, four disks or more, but there are no proofs unless the numerical results for the higher lambdas. Okay, now a bit the different result. This one by Ersch in 1963. He said if I take a big disk, and from the big disk I just cut out a smaller disk, okay, and then I need to check regarding the position of the smaller disk inside the big disk, which one has the maximum or the minimum lambda 1. I mean, which position of the small disk inside can give me a maximum lambda 1 or a minimum lambda 1. It turns out that whenever the hole or the obstacle is in the center, the lambda 1 is maximum, and whenever it's just at the boundary, touch the boundary here, so if I put the obstacle here, I have the minimum. The lambda 1 of the domain will be minimum. If I put the obstacle or the hole in the center, the lambda 1 is maximized. Okay? And with this result start really different type of problems that was called placement problems.
Sorry, may I ask something? Is lambda 1 monotone when you move from center to the boundary? Is it monotone?
From the
You mean if you follow a ray?
Yeah,
If you-
follow the ray, yeah.
from the center you follow a radius to the ray.
Yeah,
It's
it's
monotone.
monotone.
Okay, so the placement problem is like that. I consider two domains with fixed geometry. The big domain is, we're gonna call it D, the small domain we're gonna call it B. And the question is, where do I put the small domain inside, the obstacle if you want, so that to maximize or to minimize the eigenvalues, one of the eigenvalues. Okay? One of the results is 1997 he said that like the same of Ersch, but for balls on Rn, it's also correct. The other one, 2001, this is Arel and Kroger and Kurata. They show that if I have a domain with some type of interior symmetry, I'm going to just explain what do I mean by interior symmetry. Okay, so if we have a domain like that, we say that the domain has the property of interior symmetry in this direction. Means if you take like any axis here and you take the symmetry, it's inside the domain. This is what we call interior symmetry in this direction. Okay. Okay, so the result of RL was, if I take a domain with interior symmetry, so and the hole is the circular hole, whenever the circular hole is toward the center, the lambda 1 will be maximized, and when I move the hole or the obstacle toward the boundary following this direction of interior symmetry, the first eigenvalue lambda 1 will decrease, and the minimum will be attained at the boundaries.
But you did not mean those two disks to have different radii.
Sorry?
So they came out of having different sizes, the two holes. So
No, they are the same.
but
You mean this one and this one?
yeah, but they were meant to be the same obstacle.
Maybe you're right.
I see.
Actually, I take this picture from the paper, so maybe you're right. Yeah. Okay. So another paper, so the same Anissa and Idle, this is like the same, but if you take circular domain on a sphere or on a hyperbolic space, circular domains and circular obstacle, and want to move the obstacle on so it's the same. The maximum will be when they are concentric. This result with Professor El-Soufi in 2008, when we show that the same is correct for the second eigenvalue. Actually, this is a bit different because I'm going to talk later about the second eigenvalue. It has different properties. It's not always positive, lots of things. I mean, the eigenfunction is not always positive. Okay. Now, the question is, in all these previous results, we always take the obstacle to be circular. Okay, so the question was, what if I take an obstacle or the B, the domain B, not to be circular? What happened? Because on all these papers, B is a circular. So whenever we rotate it, this does not change the geometry of the domain. So it's only to locate B within the domain, or the center of B within the domain. So what if I consider a domain which is not, or a B which is not circular? What will happen? Okay, this was the question. And I started with the case of 2 square domain. So the simple thing, and then I'm gonna just state the general case. If I take D to be a square and B to be a square, and I say that the center of the 2 squares, they have the same center, and try to rotate the small square inside the big square. So this is the obstacle, and the domain is the big square minus the small one. Which position give me the maximum lambda 1, and which position give me the minimum lambda 1? It turns out that this one that we call on, it's the maximum, and this one that we call off is the minimum of lambda 1. Okay, so it's like
Lambda 1.
yeah, I'm talking about lambda 1. So this one is on, and this one is off. The on is the maximum. Okay, I'll talk a bit about the idea of proof of this case before I stated the general case. So here I have the big square and the small square inside. Okay. Big square and then the small square. I will call this position to be t equals 0, and then I will start to rotate. Okay, I start to rotate the small obstacle. So I'll get something like that. So this position, I'm gonna call it B of t, when B is rotated angle t from the original position. Okay? Okay. So omega of t, my new domain will be the big square minus the rotated small square, and lambda of t will be the first Dirichlet eigenvalue of this domain. Okay? It's clear that using the symmetry, we don't need to check all the, so t from 0 to 2 pi, we don't need to do all this. It's enough to check when t from, sorry, it's enough to check what happened for t1 from 0 to pi over 4. So we need to analyze lambda of t on this interval, and that's it, due to the symmetry. Okay? There is here a formula of derivative for the first eigenvalue, which is Hadamard formula, the well-known Hadamard formula. Of course, we can apply this for the first eigenvalue because it's simple and it's differentiable. So it's the integral over the boundary of bt. Why I only consider bt? Because the big down boundary is not changing. So I'm only deforming the boundary of the small domain. So it's an integral over dbt, the partial derivative with respect to n, and n here is a normal to the boundary at each point, n dot v, and v is a vector of the deformation. So here it's a rotation. Okay. So this is the formula. So I need to show that when I do this rotation, the lambda prime is negative. So the maximum is at t equals 0, and the minimum is at t equal pi over 4. Okay. So this was the idea of the proof, and here there are two big components of the proof. It's supposed to be yellow and green. Can you show it 2 different colors or no? Can you see? It's supposed to be 2 different colors.
It's more greenish yellow.
A1, A0 seem to go.
Okay, so I'll. Okay, so this axis is the axis. You see pi over 4 plus t. You see that I'm gonna call this one A1, the yellow, and this one A0, the green, and then this boundary is, I'm going to call it gamma 1, 1, the red, just to show. So I need to find the integral of just the formula, the Adamar formula, the integral all over this, the boundary of the small square, okay? And due to the symmetry, it's okay to integrate only from here to here, so all over the boundary of A0 and A1, and then I multiply by 4, okay? Due to the symmetry. Okay, so the first part here was to show that, and for the case of the square was very simple and clear, that when you take the symmetry of this part of A1, it's completely inside the square. Yes, this was the first part. So then it's come the part to calculate n dot v. Maybe I need to just recall what was the formula. So I need to find the sign of n dot v, and I need to find the sign of also this all over the domain. Okay. So it's actually here a real calculation. We calculate what's the product n dot v. So n is the normal to the boundary, and v is the vector of rotation, and we find that with respect to this symmetry, n dot v is always positive actually here, and it's always negative here, and it's just anti-symmetric with respect to this line. Okay, so now instead of integrating all over all the boundary, it's enough we said to integrate over here and here, and then with respect using the symmetry and using this result, it's enough to integrate only here like this. Why? Because n dot v of each point here is equal to n dot v of each point here on the other side. So it's enough to integrate only on the red line. Okay, integrate this function actually. Okay? And we know now that n dot v is always negative. This part is negative. So I need to find the sign of this function. Okay? To find the sign of this, I will introduce a new function, w of x. I'm going to call it u of x minus u of s of x. This function is defined here. And by s, I mean the symmetry. Okay? So you can see here that the interior symmetry is very important. So u of x minus u of the symmetry. There are some work here, and then we can use the properties of the eigenfunction and the maximum principle at the end, just to show that this is negative. The partial derivative with respect to the normal is negative, and then I just plug into the formula, and I find at the end that lambda prime is always negative. Okay, and this allows me to say that the position 0 is the maximum position, and the position pi over 4 is the minimum position. And this is just the idea of the proof on the case of the square. And after that, I'll just I will announce the general case. So this same result could be extended to like domain that are invariant under the rotation to pi over 2n. And the other property is that the boundary of the domain is like increasing between two axes of symmetry. I'll just give an example. This is an example, so you can see that it is here n equals 6, so it's invariant under rotation. And you can see that between two axes of symmetry, the boundary is a monotone. So here is decreasing, here is increasing, increasing, and so on. This is another example with n equals 3, another example with n equals 6, and of course there are also many examples. So the idea is that between two axes of symmetry, just the boundary is monotone, either increasing or decreasing. And I'm going to call these corners the exterior corners, and this one the anterior corners. So now we just take D and B, both of them, they satisfy the same properties. So D and B are both domains of this form, and we can see that, same as for the square, the position on is the maximum lambda 1, the position off is the minimum for lambda 1. So here's an example with n equal 2. Here's an example with n equal 3. So this is the on. You can see that the interior corners are on the same axis. The exterior corners are on the same axis for the position on. For the position off, you can see interior, exterior, exterior, interior. This is another example with n equal 4. So that's it for the first eigenvalue. Now the next step was I was trying to do something similar for the second eigenvalue for lambda 2. And with lambda 2, the problem is that first of all the second eigenfunction, as you know, changes sign inside the domain, so it's not always positive. So it's not really possible to do this this trick of interior symmetry. And then the second thing, which is very important, is that it's not really simple. So the formula of derivatives doesn't apply directly as for the first eigenvalue. Then we should find different techniques to work with the second eigenvalue. Okay, in a paper about the second eigenfunction, the one with the disks, the idea was to show. The idea on this paper, so we showed that the same result of Erg, but for the second eigenvalue, we showed that this position is the maximum for lambda 2, the second eigenvalue, and the other one, and when the obstacle in here, this is the minimum. The idea here was.
Sorry, is lambda 2 also monotone when you shift?
For this
second eigenvalue,
yes.
It's also monotone.
Yeah, this is the idea of the proof. So here, actually, what we did is that we know that the lambda 2, when we symmetric, the lambda 2, when we take a symmetric one, it has 0 here, and then it's positive here, and then it's negative here. And the idea was to consider only this domain, the upper part of the domain, and remove and just move the whole. And it's just exactly similar. The proof here is exactly similar to what we did with lambda 1. Why? Because my eigenfunction is positive here, so I can apply the same. The same technique. Okay, so I'm working on half of the domain. So it's very important to know where the second eigenfunction is actually 0, and where it's positive and where it's negative. Okay, so I mentioned this result to tell you that from here it was my motivation to explore this nodal line of the eigenfunction. Nodal line means where the eigenfunction is equal to 0. To check what's the geometry of this nodal line. And turns out that this was actually, there are lots of results and many works about the geometry of this nodal line. First of all, we just the nodal line, so this is the closure of the points where second eigenfunction is 0. This line, when we're talking about the second eigenfunction, the line is a simple curve, and by Courant's nodal theorem, we know that there are only two nodal domains of the second eigenvalues. No, then there is the domain where the second eigenfunction is positive, the domain when the second eigenfunction is negative, and there's the separation between them, the 0. And this line is called the nodal line, and lots of works to see the geometry of this line. We start by the conjecture of Payne, who said that this nodal line, in case of plane domains, it intersects the boundaries into exactly 2 points. So here I'm talking about any plane domain. This was the initial conjecture of Payne. So any plane domain, remember that the nodal line cuts this domain into two different subdomains. Okay, one where the eigenfunction is positive, one is negative. So the conjecture was that, of course, this nodal line must touch the boundary into 2 different points.
Sorry, do you assume simple connected domain here?
Sorry?
Do you assume your domain is simply connected?
This is the conjecture of Payne, just simply the initial conjecture was for any domain. The initial conjecture of Payne, that for any plane domain, it touched the boundary into.
But
into 2 points.
doesn't you think construct as counterexample, because nodal line touches at 4 points, right?
Yes, wait.
Yeah.
Ah,
Wait.
Actually, what he said exactly, the conjecture that the nodal line cannot be closed inside.
okay.
Okay? Yeah, so I'm sorry, this is so it cannot be closed. So in this case, it should be, like it cuts, it touches the boundary into different points. So this is the point, that it cannot be closed inside the domain. Okay? Okay, so he proved this. He proved this conjecture later for a special type of domains that are symmetric and convex in one direction. What do I mean by convex in one direction? Like, I'm sorry, I need to use the board again. Convex in one direction means that if you take a domain like that, this is symmetric. Should be symmetric. Convex in this direction means if you take any line perpendicular to L, you see that the intersection is connected. So this is convex in this direction, but this is another example of a domain which is not convex, like this one, for example. If you take this, you can see that so it is convex in one direction, not the general definition of convex domain that we know. So this is not convex in this direction, but this one is convex. Okay, so Payne showed that for this type of domains that are symmetric and convex in one direction, of course, the nodal line touch the boundary in 2 points and cannot be closed inside. And then there are another result of Lin when he showed that for domain with invariant under rotation, so it's a type of dihedral symmetry as well, also the nodal line should touch the boundary in 2 points and cannot be closed inside. And more general result of Alessandrini, he said that any convex plane domain has this property. Okay? And more recently, also this property, the conjecture of Payne, is true for set of concave domains, some of them, not all. Okay, but there is a counterexample proof that this conjecture is not always true for any domain we take. There are Hoffman, Ostenhoff, and Dirichlet who constructed an example of a plane domain, such that the nodal line is actually closed. But their example was actually kind of disk, and from the disk we remove these arcs. Okay? So it's not simply connected, not anymore simply connected. And they showed that here the nodal line is some kind of closed curve here, so it does not touch the boundary. But it's not not a simply connected domain. Okay? There are also another example, but in higher dimension of domain with a closed hyper nodal surface. Actually, we call it.
Sorry, was it counterexample? I mean, is it one Hoffman Ostenhoff or two Hoffman Ostenhoffs? I
Two
thought
of
there
them.
were two.
Two of them.
Two of them.
It's Maria and Thomas? Or it's Thomas?
No, both Thomas and Maria. Okay. So after this after I see this counterexample, so I also ask myself the question: if I take domains with holes, the same as I'm working with, so what kind of geometry can the nodal line can have? And this is I'm just announcing the result. I found that if the domain has the symmetry and the convexity in one direction, similar to Payne proved at the beginning. So if D and B, both of them, have the symmetry and the convexity in one direction, and if they have only the symmetry in the second with respect to another axis. So in this case, we'll be sure that actually the nodal line touches the exterior boundary and the interior boundary, both of them. And just quickly, this result I use it to actually found with this type of domain. So it's not it's not disks anymore, type of ellipses, for example, or other example. There are other example, and in this case, I can show that the maximum of lambda 2 is really attained on this position. That's it. Thank you.
Well, any questions or comments? Please go ahead.
Well, let's say we take things with two squares, but we allow the inner square just move in whichever way we want. I mean, to shift and to rotate. Do you know what is maximizer, what is minimizer?
Still, we don't know. No? Because we lose the interior symmetry, we lose the symmetry, everything, so we don't know.
Do you know numerically?
No.
If you
Tell you the question. I think.
what is the same? If you only shift,
The square without rotating.
so if both have the same orientation, the little one and the big one, you only shift, so you have an analog of Hirsch's results for anything other than circles.
I haven't seen any result like that, actually. And following the same techniques, it doesn't work. So I try with it, it doesn't work.
I would like to know triangles. That's where we were stuck.
So if you allow the triangle to move, not only rotate,
Only move, yeah, only translate.
but it's interesting to know. Yeah.
And I take it if your inner square is so large that you cannot really freely rotate it, then
Yes.
one of the extrema will be one that touches the.
Yes. So
Okay,
one
because
of
it's
one of the condition, of course, that when I rotate, it should be inside. Yeah. But I didn't mention it here, maybe explicitly.
Other questions or comments? Well, let's thank you for that. So I think